So what clone size do you prefer? Because in organic chemistry, size actually matters.
Hello, it's Maciek from Chemicals, the new monthly series from CNDN. Let's talk about the chromatography.
Chromatography is one of the most powerful techniques we use to separate mixtures in chemistry. When a reaction gives us several compounds at the same time, which is usually the case, chromatography allows us to separate and isolate them in a pure form. To see how this works in practice, let's start with the simplest version: thin layer chromatography. On this silica TLC plate, the colorful spots represent different compounds. Each travels a different distance because of its polarity. Less polar spots rise higher, more polar ones stay low. When the separation is simple and the impurities are very polar, a fast cleanup with a silica-filled funnel can be enough. The product flows through while polar byproducts stay on the silica. Sometimes it works beautifully like this fluorescent compound. Other times it gives dark, messy residues that still need a proper purification. That brings me to the Sonogashira coupling. Here's the crude, dark post-reaction mixture and the bright clean product that's hidden inside it. Chromatography is what makes it possible to uncover this pure substance from such a murky mixture. To see what we are dealing with, I ran a TLC showing the substrate, the complex crude mixture, and the product. To separate this mixture, I will use a chromatography column. Silica gel is very polar, so it interacts strongly with polar compounds, while less polar molecules move through more quickly. Because the compounds attach to the silica with different strengths, the mixture spreads out when the solvent flows. I chose the solvent system based on TLC, mix it with silica to make a slurry, and pack the column. Then I load the crude mixture and start collecting fractions. To see what's in each one, I spot small samples on TLC plates. The plates contain a fluorescent indicator, so under UV the background glows while any compound that absorbs that light appears as a dark spot. This makes it easy to track the product and find the clean fractions. When I've defined the pure fractions, I combine them and remove the solvent on the rotary evaporator. After concentration, I left with a clean flask containing the isolated product. To confirm purity and identity, I record the NMR spectrum. The changes in the signals show how the structure has transformed. Here are the spectra of the starting material, the crude mixture, and the purified product. Comparing them clearly reveals the reaction progress and confirms that we isolate the final compound. Thanks for watching this chromatographic journey. Join me again next month for another Chemicals episode from CNDN.